most of you have probably heard of, and some of you used, Nonpareil, which is, I like to refer to it as the world's first open source microcode level HP calculator simulator. There were, in fact, other microcode level calculator simulators for HPs prior to that, but they were actually developed inside HP and they were not open source, and generally most of them were not available to customers at all, the exception being that they offered a financial calculator program that came with the HP 150 desktop computer, and that it looked like a 12C. That was because it actually simulated the 12C internals. So I actually started working on simulating the internals of HPs around 1981, and at the time the PPC, various members had started figuring out the innards of the 41C, and so I started simulating that on an Apple II. The simulator actually ran slower than an HP 41 at that time because the Apple II, while it was an amazing machine for its day, was not particularly brisk. But in 1995, I decided to pursue this project more seriously and started simulating the HP 45 and 55 based on information out of patents primarily, but also some information out of HP journal articles and other sources. And that was called CASM-SIM, or CASM-SIM. And then also the 41C, the innards of which are much more well known thanks to the efforts of people that contributed to PPC and CHU and so forth, called NSIM. And the innards were different, but the user interface code was fairly similar. And so I ultimately realized, well, I should just because I wanted to simulate more models as well, I should just combine these. And so I released it as open source under the GPL2 license. And over the years, added more models. I'd kind of had the vision that, wouldn't it be neat if someday I could simulate almost all of the HP calculator models that came out of Corvallis division and prior to that, Advanced Products division. And I wasn't so much interested in the desktops, like say the 9830 or the related models, but mostly the handhelds or the desktop printing ones that were closely related to the handhelds. And that, because there was no documentation on the innards of most of those calculators, that seemed like just a completely pie in the sky sort of dream that, well, I'll never actually be able to get there. And it's true that there are still a few, notably the HP 10 KISS handheld printing four-banger that for technical reasons I don't have any information on the innards of that and can't currently simulate it. But it turned out that there were few enough general architectural variations that I was ultimately able to figure out how to simulate almost all of them. Along the way, though, over the years, I had some ideas for how I wanted the inside of Nonpareil to work, and not all of those panned out, and a lot of complexity appeared, and built up essentially significant technical debt to the point where I really no longer like to work on that code base very much. And I decided, well, it's time to rewrite it and get rid of some of the cruft that's accumulated and start from a better architectural base. And of course, what happens, if any of you have worked in the software industry, is there's something called second system effect. And that, you decide to throw away your code and do something new and clean and better, and either it never comes to fruition, or it ends up being just as crufty and bad as the original. And over time, that will likely happen, but at least we get a fresh start. You can try to avoid some of the mistakes that were made the last time around. Now, one of the other problems is that, I don't know how to work this thing. Oh, that's all right, I don't need it. One of the other problems is that a lot of people ask me for Mac support, and even Windows support, let alone Mac support, was pretty difficult to do with the original code base. As I said, I used the GTK Plus toolbox, which was open source and in principle supported Windows and Mac, but really ultimately not very well. They were, I hesitate to even call them second-class citizens in GTK. They were really more like third or fourth class. So I decided to rewrite in C++. I mentioned this last year. I'd started on it basically about 2 years ago now. rewritten in C++. The old code, even though it was written in C, was somewhat object-oriented, but in C, the language doesn't provide any support for object orientation. You have to do it yourself with your own arrays of pointers instead of behind-the-scenes V-tables that C++ gives you, and so forth. Using the Qt6 toolkit, the latest version of Qt, which is arguably both a more powerful toolkit than GTK. It is natively C++, so it actually is not practical to use it from C, but it supports Python really well. And Qt generally both looks pretty nice and actually does run well on Windows and Mac OS. That's because the company behind the commercial version of Qt makes money selling it into those environments. So naturally, they're going to put more effort into that than people doing just a purely open source thing that primarily is on Unix systems. So a few more comments there. The notable difference is that Nonpareil II, at least the first, will not be open source. It may be open source at some later date, but I actually want to try to sell it and recoup some of my time investment in it. Also, though, I wanted to use scalable vector graphics. Nonpareil, along with a lot of the emulators, used bitmap graphics. And if you have a bitmap representing the calculator and you want to show it on screen, to look nice, it needs to be either the resolution it was designed for or an integer multiple of that. And you try to scale it arbitrarily, and you get variable results, and it's not always great. So obviously the modern standards for graphics are all vector oriented, and I wanted to use vector graphics. And so I have Nonpareil II, at least partially working. I have vector graphics. It looks really nice. I can scale it. I think I showed some last year. We'll more easily be able to support more calculator models, add-ons, better I/O. So supporting that graphics, each calculator has a master SVG file that contains all the graphics for it, but you can't just dump any old SVG file you can draw in any old program you want into it. It has to be structured and with elements named in a particular way that the software can actually figure out what elements within that SGV file are the keys and display segments and so forth. So it will be possible for other people to create alternate SVG files if they want to, but I haven't really documented how to do that. And the best way to do it is just going to be to look at the ones that I provide and see how they work. And they're not complicated. So I've run into some difficulties with the code. Now, I first learned some C++ in 1989 to 90. I worked briefly at Apple Computer, and they actually sent me to C++ training. This was before there was an ISO standard for C++. So it was a very early version of the language, and they trained me for it. And then I never had any occasion there or in my employment for a long time to use it. And so 2 or 3 years ago, I got hired into a job that was programming C++, and I had to explain to them, well, they had my resume, which didn't show a whole lot of C++ experience, and so I specifically went out of my way to tell them, well, you want C++, and I know a little of that, but my experience in that is all very much out of date. And they said, well, that's okay, because we don't use a whole lot of the features of C++, and you have a lot of the other skills and knowledge that we're looking for. I had a lot of other buzzwords on my resume, and so I did use C++ there. And they were correct. They didn't use a huge amount of the language. It's a very big language nowadays with a very big library, and the library contains a whole lot of very useful stuff. But it's pretty intimidating to somebody either just starting out or who's only used really ancient C++ that didn't have anywhere near that much stuff. So over the last 3 years, I've become somewhat more familiar with it. Tip, when programmers are interviewed for jobs, they often will say, okay, on a scale of 0 to 10, rate your knowledge of such and such, maybe a programming language or a library or whatever. And tip I offer is anybody that comes along and is asked that question and says 9 or 10, they better be either Bjorn Sustrup, who invented the language, or a member of the actual C++ language committee, because anyone else who says 9 or 10 in answer to that question is lying. There may be 24 people in the world that could accurately say that. Now, of course, I know resume inflation, and you don't want to sell yourself short, and so, you know, if I answer in an interview realistically that my level of expertise in C++ on a 0 to 10 scale, where of course 10 is the most experience you could possibly have with it, if I try to realistically say it's 5, people are going to say, oh, well, we don't want him, he doesn't hardly know it at all. So that's difficult. But anyhow, current status, I am having a difficulty involving multiple inheritance, and I won't go into details. And I've had trouble debugging it because one of the things about C++ and being object-oriented is your symbols all get mangled, and the debugger demangles them for you. But basically, the flip side of the convenience of polymorphism, which is what object orientation gets you, is it makes debugging more difficult. And I think there's no fundamental way around that. At least nobody seems to have invented any means of debugging it that it is not more difficult than normal programming. One of the developers of, I forget, either C or Unix once said, programming is difficult. And so when you program, if you write a program as cleverly as you can, and debugging is twice as difficult as programming, then you by definition are not capable of debugging it. And this is something that experienced programmers learn is you never want to use a super clever solution to something. You want to use a simple, obvious solution to it unless it's just absolutely necessary to squeeze the most performance out of it or the most something. And if you do that, then you want to document the heck out of it. So, work on Nonpareil II has led to a side quest, which was because part of the architectural objective was to make it easier to add expansion. One of the things I'd never done yet in Nonpareil was actually have it do HPIL, either with a physical interface or virtual HPIL that some of the other emulators use. So I wanted to do that, and so that led me to the side quest of writing a C++ HPIL protocol stack. And I said about that, I won't say differently than everyone else has done it, but a little differently than most people do it. And I'm referring not just to a stack that runs in an emulator, but also actual implementation of HPIL devices. Now, the reason is that HPIL specification defines HPIL. It was modeled on the HPIB specification, which also became known as GPIB or IEEE 488. That was a parallel bus. HPIL is, in a sense, a serial version of that. And so the specification was written, modeled based on that, and it splits the architecture up into 14 interface functions that handle different parts of the HPIL protocols. And so some of those interface functions are mandatory for all devices, and others maybe are only present if the device is intended to be a controller or if it supports, let's say, power down modes, or there are a bunch of different optional features. Technically, an HPL device should come with a string that represents exactly which HPL specification capabilities it has. The HP ones, that was typically in an appendix in the user manual. Some other non-HP devices have that string in the documentation, some don't. And that I didn't mention on the slide, but that's actually one of the things I wanted to do, is the configuration of my HPL stack is based on providing that actual string when instantiating the stack, and that controls what interface functions it instantiates and what subsets of them and so forth. So the specification, each of those interface functions is defined as one or more state machines. HP just refers to them as a state machine for the function, but really it might, some of them, because the state diagrams they'll show one diagram, and normally a state diagram is a directed graph, so you have some number of nodes, which are the states, and you have directed arrows from those nodes to other nodes that represent different states, and those arrows will be annotated with under what condition that transition is made. But if your graph is multipartite, if it is disjoint, then you actually have multiple state machines, and this is the case for some of these HPL state machines. So the 14 interface functions actually turn out to be something like 21 state machines. Now, HP in the documentation kind of implied that if you're going to build an HPIL device, you need to implement these state machines as we have documented them. But they also say you're not actually required to use these state machines as long as the behavior of your device is equivalent to if you had used them. Well, one of the obvious thoughts about that is, well, the easiest way to make that guarantee that it behaves as if it implemented the state machines is by implementing the state machines. So many HPAL implementations do not do that. And the reason is, well, there's a couple of reasons. Now, here's kind of a digression on that. Part of the 4 lowest level state machines in HPAL are actually implemented in the 1LB3 or 1LB6 chip that is inside all HP's HPAL devices. And so that requires that the host side of that that's going to talk to that 1LB3 chip can't implement those particular functions in the same way as if it was talking directly to the actual physical wires of HPIL. So they document in the chip specification what you should do instead for those. But the reason you might not, okay, here's been another digression I'm going to skip actually, but the reason you might do an ad hoc implementation instead of actually implementing the state machines as described is you might be using a microcontroller that has almost no memory. And this was the case for HP's own early HPAL devices. They used a MOSTEC MK3870 microcontroller, which is based on the Fairchild F8 microprocessor. And they generally had only 1K byte or 2K bytes of ROM and only 64 to 128 bytes of RAM. And so implementing those state machines as documented would have used up a substantial amount of the memory. So instead, they did an ad hoc approach. They didn't publish the source code to any of that. Some of you may have seen someone managed to dump the 3870 chip out of an 82143 printer. That is not the IL printer. That's the 41's pre-IL printer. But it uses the same MK3870. And since they dumped that ROM, I started working on reverse engineering, exactly how does this thing work. My work on that is up on GitHub. It's not complete, but there's some insights to be had from that. So Mountain Computer actually did implement the state machines in some of their devices, and they actually had a paper presented at a conference many years ago, which I only know about because it was in the proceedings, and so this is probably on your flash drive. But they described how they implemented it. This was using an 8048 family microprocessor, and they did that in a couple of different devices. So I decided I'm writing a brand new HPAL protocol stack in C++. I'm not going to try to do the ad hoc approach. I'm going to do it exactly as the protocol specification manual describes. And right now, that's intended to logically implement, okay, HPAL, the messages that go over the wire are called remote messages, and they consist of 11 bits, the first of which is a sync bit. The first 3, including the sync bit, are a class of message, and the remaining 8 bits are either a data byte in the case that it's a data message, or if it's a command message or the like, then it's an encoding of some command. And the actual 1LB3 chip starts processing those bits of the remote message as they come in. It doesn't wait till all 11 of them have come in. That's in contrast to, for instance, virtual HPIL, that the whole message comes in at once or is sent at once. So right now, my code doesn't support using an actual 1LB3 chip. It's written in terms of either complete remote messages or individual bits of messages. It supports either one. So the status, I've been testing this HPAL stack for a little while with simplistic test cases where I have 2 HPIL things that are logically kind of separate devices, but they're all inside my one process in the computer. They will be in separate threads as I make more progress on this, but they're built to have exactly the capabilities needed for a particular test case. Like if I want to test, okay, does a asynchronous ready message get sent when it's supposed to, and is it handled correctly, by another node when it's supposed to? So I have not yet tested with any actual physical HPIL devices or with existing virtual HPIL. That's on the radar. So that's I am going to release that. It'll be part of Nonpareil II, but I will also release that separately under a fully open source license. And I'm not trying to recommend that anyone else necessarily wants to use my HPAL code as is, and few people are developing HPAL devices these days. However, there are reasons somebody might not want to, but if somebody wants to, it'll be under a license that allows that. And I'm not claiming that this is better than other implementations, but what I kind of wanted to do by following the specification pretty closely in terms of those state machines is make this somewhat of a reference implementation, because HP did not publish a reference implementation of HPIL, only the specifications. To their credit, the specifications are very detailed and for the most part, extremely well thought out. And back to just C++ in general, I mentioned that I started out with a really early version that was actually pre-standard, and the first standard was, I believe, 03, or no, sorry, it was 98, and a little bit of improvement in 03. And I claim the first usable version of the standard for real software development, or I hate the term, but software engineering, is C++ 11, because it provided usable memory management in the form of smart pointers. C++, unlike say Java, does not generally have garbage collections. The programmer has to manage their memory, and otherwise you get leaks or data corruption or various other horrible problems. And so any feature that a language can provide that provides some automation or at least help in managing memory is very worthwhile. Some of you may have seen that the current US administration has actually been beating the drum for trying to move software development to to memory and type safe languages, which will reduce the number of faults in the programs, reduce the attack surface, reduce of the faults that do exist, typically reduce a lot of them, like a lot of privilege escalation attacks, to denial of service. You can't completely eliminate denial of service attacks, but that's better than leaking other people's data, like credit card numbers, or a lot of other desirable actions. So it's interesting that there's finally some impetus in the software world, and Microsoft, of all people, is actually pushing heavily on this themselves to start using a safer language. C++ today is not one of these type-safe languages. However, as Bjorn Stroustrup himself points out, inside C++, which is a huge, sprawling, complex thing, there is a smaller, simpler, more elegant language struggling to get out. Well, I generally discount that statement, because that smaller, simpler language struggling to get out had to have asphyxiated 20 years ago. But there is now, the Standards Committee has accepted a working paper on implementing a safe version of C++, something I never thought was going to happen. And not only is there the working paper, there is it's technically, because it's not accepted in C++, it's another language called Circle, but it essentially is safe C++. So there is hope for the future of C++ becoming safe. Now, I generally use C++ 20 because it has a lot of nice features. The job I had most recently programming C++, their standard was we use C++ 14. If there's some nice feature in 17 or 20 that you can justify, we should use it, it would actually save us time, money, whatever, then we could. For my own use, though, I have standardized on 20, so not the latest, which is 23. But the key part here is there are the top 3 C++ compilers in the world: Microsoft Visual C++, GCC, it's technically G++ from the GNU compiler collection, and Clang, again for C++, that's technically Clang++. And those support most or all of C++ 20, the entire language, but they maybe don't have some of the dark corners of the library. And they all support, a fair bit of C++ 23, but not all of it yet. So C++ 20 is a pretty good target because it's well supported in the world. And so I decided, okay, it's safe for me to use the features of 20. And yes?
You got to wind down. We can only use the room until 10 because there's people above us in hotel rooms.
Okay, well, all right. I guess I can skip the other material then. What's that?
I said, when you're done, we'll clap quietly.
Well, what time is it now?
10.
Oh,
10?
okay, well, I guess that's it then.
To be continued.